Chapter 10b, the shape of molecules. In considering the shape of molecules, we can use certain rules to determine this. Lewis theory, in combination with valence shell electron pair repulsion, VSEPR or VSEPR theory, can be used to predict the approximate shape of molecules. VSEPR theory is based on the idea that electron groups, that is lone pairs, single bonds, multiple bonds, they repel each other. This repulsion between the negative charges of electron groups on the central atom determines the geometry of the molecule. So we see a few interesting molecules, certain shape for water, certain shape for carbon dioxide, linear for oxygen, another shape for water showing it's kind of negative here and kind of positive there. What if you were asked to predict the shape of carbon dioxide, which has the Lewis structure and is written, it has double bonds. The geometry of carbon dioxide is determined by the repulsion between the two electron groups, this bond pair on the central atom and this bond grouping on the central ion. They get as far apart as possible as they can because of their repulsion, and that turns out to be 180 degrees, making then carbon dioxide a linear molecule. Predicting the shape of carbonic acid. Here's the Lewis structure, and around the central atom you can see that we have three groups of electrons. We have this bonding group and this bonding group and this double bonding group. So since it has three electron groups around it, they'll try to get as far away as possible, resulting in 120 degrees apart. And this molecule is given then the name of trigonal planar. Three apexes all in the same plane, trigonal planar. If a molecule has four electron groups around the central atom, as does methane CH4, it has tetrahedral geometry with bond angles of 109.5 degrees. Here's a look at a tetrahedron. It has four triangular faces, and you can see that the angles around the central atom are the 109.5 degrees, all of them. So this equal repulsion drives them apart as far as possible, 109.5 degrees. How can you predict the shape of molecules with lone pairs? Let's take an example, such as ammonia, NH3. Here's the Lewis dot formula for ammonia. You notice around the central atom there's four electron groups, but one of the electron groups is a lone pair instead of a bonding group. What you do is that with the four groups you arrange them like a tetrahedron, but you note that this group up here is a lone pair and there's no atom. So when you describe the geometry of the atom, it looks like this, and it has a different term. It's no longer a tetrahedron but a trigonal pyramid. A trigonal pyramid because the base of it is a perfect triangle, equilibrium, and then the apex above making it a pyramid. So a trigonal pyramid. Here's a table, 10.1, very important one. All you have to do is write a correct Lewis structure, identify the electron groups, and it will give you then the angles and the description of the molecular shape. You can always look it up here. Predicting geometry using VSEPR theory. First of all, draw a correct Lewis structure of the molecule. Then determine the number of electron groups around the central atom. Then determine which ones are bonding groups and which ones are lone pairs. And then refer to table 10.2 to determine the electron geometry and the molecular geometry. Representing molecular geometries on paper. Many chemists use this notation for bonds to indicate three-dimensional structures on a two-dimensional paper. Like a straight line means it's in the plane of the paper. A dashed line means it's projecting into the paper, behind the paper, a bond projecting out of the paper. Here's the way these structures look. For the linear, everything's in the plane of the paper. For the trigonal pyramid, everything's in the plane of the paper. Same for the bent. However, in the tetrahedra, we have in the plane of the paper these two, but this one is projecting behind the paper and this is projecting in front of the paper. The wedge formulas. And same with trigonal pyramid. You see which one's projecting out and projecting behind. Here's another sketch of the tetrahedron showing the wedge formula. That if this is in the plane of paper, this will be behind, this will be coming out. Or here's ammonia showing the trigonal pyramid. Behind the plane, in front of the plane. What does electronegativity and polarity have to do with the fact that oil and water don't mix? Well, if you combine oil and water, you get an image, something like this, oil floating on top with the water below. Something about water molecules causes them to bunch together one area and oil the other way. Electronegativity and polarity, why oil and water don't mix? Well, the two bonds between oxygen and hydrogen consist of an electron pair. These right here, these are the bonding pairs, shared between hydrogen and oxygen. However, the oxygen is more electronegative. It means it attracts electrons more. So the electrons get pulled toward the oxygen, leaving this partially positive and this partially negative, thus making this a polar bond and resulting in a polar molecule. This end of the molecule is negative, this end of the molecule is positive. The ability of an element to attract electrons within a covalent bond is called electronegativity. Oxygen is more electronegative than hydrogen, so that's why oxygen has the lion's share of the bond pair in water. Here's what it would look like. Here is the oxygen-hydrogen bond, but the electrons are being pulled over toward the oxygen, making it partially, this is the Greek letter for delta, partially negative and partially positive for the hydrogen. This is called if the whole molecule is polar, it possesses what they call a dipole moment, a separation of charge within the bond. Polar covalent bonds that aren't equal sharing, that have a dipole moment, are called polar covalent. And the size or the magnitude of the dipole depends upon the polarity. And that depends upon the difference in electronegativity between the two elements in the being bonded together. For a fixed bond length, the greater electronegativity difference, the greater the dipole moment and the more polar the bond. The value of electronegativity is just a rating scale. It's not based on any measurement. It's the most electronegative element is fluorine, with electronegativity of 4. Linus Pauling introduced the electronegativity scale used here, and he set the electronegativity of fluorine at 4 and computed all the others relative to fluorine. Here's a grand map of the periodic table with its elevated. You can see the tallest one is fluorine with electronegativity of 3, and it just, as you go across to the left in the period, you get 4, 3.5, 3.0, 2.5, 2.0. As you go down, it decreases. You get 4, 3, you get 3.5, 2, etc. So the most electronegative element is fluorine, and in this region, they attract electrons. Hydrogen attracts them a little bit, about the same as carbon. And these metals, they don't attract, they're rated very low, very weak, electronegative. If two elements are identical electronegative, then there is a perfectly covalent bond. they have equal share in the bond pair in between them. So, for example, in the chlorine, which is a dimolecular element, it's nonpolar. If there's a large electronegative difference, then not only does the more electronegative element, such as chlorine, attract the electron, it actually takes the electron, becomes negative, leaving the other part of the bond positive. So we have an ionic bond. If there's an intermediate difference in electronegativity, then you have this situation of polarity. Here's an example of HS, hydrogen fluoride. Hydrogen is sort of less electronegative than fluorine, so fluorine takes most of the electron, but hydrogen has some part of it, so we have a polar covalent bond. The effect of electronegative difference on bond types is if there's no difference, then it's purely covalent. If there's intermediate difference in electronegativity between 0.4 and 2, then it's polar. If it's larger than the difference of 2, then it's clearly an ionic compound. So you can look up on the table what the electronegativity of each atom in a bond is, and then take the difference and identify what type of bond that it is. Does the presence of one or more polar bonds in a molecule always make a molecule polar? The answer is no. A polar molecule is one in which the polar bonds add together. If they cancel each other, you don't have a polar molecule. When it's a diatomic, there's no possible cancellation, so if it's a polar bond, the molecule is polar. For molecules that with two or more atoms, it's more difficult. You have to tell the polar molecules from the nonpolar ones, because there might be two or more polar bonds. They may cancel one another. Here's an example. Carbon dioxide. This is definitely a polar bond between carbon and oxygen. So you got a polarity to the negative here and a polarity to the negative here of the same magnitude or size, and they actually cancel each other, and so the net polarity of carbon dioxide is 0. Carbon dioxide is a nonpolar molecule. So it's like vector sums. You have to know if it's a tug war of this way and that way and it's equal, they cancel. Water, however, is polar. You've got the polarities equal, polar bonds of hydrogen and oxygen, but they don't cancel each other because they're both pulling sort of in the same direction, netting a polarity that way. The difference electronegativity between oxygen and 1.4. So water has two dipolar moments of the bonds, and they cancel. So here's the way this cancellation works. If they're identical polar bonds 180 degrees apart, nonpolar. If they're identically polar bonds 120 degrees apart, then the molecule is nonpolar. However, in the case of trigonal pyramid, if they're identical polar bonds, but in the directions, not in the 120 degree direction, they're not pointed in the right direction, then they cancel. So two polar bonds at an angle, they will not cancel, and so therefore we have a polar molecule. However, a tetrahedron, in which you have the same polarity in all four bonds, they all cancel, you can have a non-polar molecule with polar bonds. How does soap work? Well, if you look at the soap molecule, you'll see that one end of the soap molecule is polar, and it attracts water. The other end attracts grease because it's nonpolar. So what happens is when you put the soap in with the water, the grease gets kind of attracted to this end, and then stays in the water, and then when you rinse it away, the soap molecules, they carry the grease away with them, cleaning your greasy clothing or spots in their clothing. So briefly, Chapter 10 in review, we learned about Lewis theory and writing Lewis dot structures and seeing how bonds are formed. We know there are two kinds of bonds, the ionic bond and the covalent bond. And we know that atoms act so as to obtain noble gas electron configurations or have complete octets. We learned about molecular shapes. The shapes of molecules can be predicted by using Lewis theory. That is, writing the Lewis structure, looking at the center atom and seeing how many electron groups form around the atom and what shape they take to take care of the repulsion between electron groups. We learned about electronegativity, which is a relative ability of elements to attract a bond, and we know that electronegativity increases as you move to the right in the periodic table and toward the top. Fluorine is the most electronegative element. And we learned that electronegativity can tell us about polarity of a bond, because when two atoms are bonded together, if one has a higher electronegativity, it attracts the electrons toward it that are in the bond, making it kind of negative, and the other remaining partially positive. In diatomic molecules, a polar bond results in a polar molecule. However, in more than two atoms around a central atom, these polar bonds may actually cancel. For instance, 4 polar bonds in a perfect tetrahedron will cancel. So the skills you need to practice in this chapter is predicting the shape of molecules, determining whether the molecule is polar, but also you need to be able to write those Lewis structures and understand the predictions of valence shell electron repulsion theory, VSEPR theory. So have fun studying.